Hello everyone, I'm Liu Yunlong from Xidian University. Now I will give an introduction about our work, low-light image enhancement with multi-stage residual quantization and brightness aware attention. Now, most deep learning-based low-light image enhancement methods focus on learning the mapping function but ignore the guidance of the auxiliary generative priors provided by normal light images in the training dataset, leading to unpleasant artifacts or distorted colors in the enhanced images. Recently, some phase restoration methods have proposed learning texture and details guided by a vector quantized codebook prior. Decoders based on VQ networks simultaneously store rich high-quality textures and details, thus demonstrating improved visual restoration results. The VQ-based image restoration methods contains two stages. The first stage, training of the high-quality codebook. The goal of this stage is to train a codebook that contains high-quality features along with its corresponding decoder. The stage 2, training of encoder ELQ. In this stage, the weights of the codebook and D are fixed, and the training focuses on ELQ, aiming to make ZELQ to closely approximate ZE. Different methods may use various approaches to fuse ZELQ with ZQ, achieving better restoration results. If this method is directly transferred from phase restoration to low-light enhancement in natural images, several issues will arise. The method requires downsampling compression of high-quality images by a significant factor to obtain ZE. This leads to loss of image details and can result in unstable network training. Compared to phase images, natural images have richer textures, which necessitates the construction of a more diverse codebook. And there is a gap between the low-quality features ZELQ and the features in the codebook for high-quality features, making the matching between ZELQ and the features in the codebook unreliable. Shortcuts commonly used in encoder-decoder structures cannot be applied to VQ-based networks, leading to significant further loss of details. To address the issue of significant information loss due to high compression rates, we employ residual quantization to build the codebook at a lower scale. Residual quantization represents features by summoning multiple codebook features, thereby offering greater expressiveness. To address the gap between dark feature and normal light feature codebooks, we proposed a query-based matching approach. This involves constructing a trainable parameter queue, which calculates similarity with dark light features. Using this similarity, more reliable features are selected from the codebook. To mitigate information loss, we introduce a fusion branch that combines the outputs of the encoder and the decoder at different scales to supplement missing information. We have designed a brightness-aware attention module that learns brightness mapping to modulate features, enhancing the network's robustness to brightness changes. The network is divided into four main components: the encoder EL, the decoder DN, the residual quantization module, and the fusion branch DF. The fusion branch DF combines the above 6 features and outputs the final enhanced result. The encoder EL encodes the input low-light image at 3 different scales to obtain FEL, FRL, and F3L. F3L is subject to residual quantization to produce FQL, which is then decoded to obtain features at 3 scales: FED, FRD, and F3D. The fusion branch DF combines the above 6 features and outputs the final enhanced result. The network training consists of 3 stages. The network in the first stage includes a normal illumination encoder EN, a residual quantization module with a codebook C, and a normal illumination decoder DN. The objective of the first stage is to learn an expressive codebook C and a price decoder DN. In the second stage, we introduce a query module Q to learn the feature similarity based on the features of the low-light encoder EL and the learned queries Q. The parameters of the encoder EL and the queries Q need to be trained, where the codebook C and the decoder DN learned in the first stage are fixed. In the third stage, we proposed a fusion branch DF to merge the pre-trained features of the encoder EL and the decoder DN. This further preserves valuable details and achieves better performance than the second stage. In the first stage, the input is a normalized image and the output is a reconstructed normalized image. The objective of this stage is to learn an expressive codebook C and a decoder DN. The loss function for this stage is defined as follows. In the second stage, the input is a low-light image and the output is an enhanced image. The parameters of encoder EL and the queries Q need to be trained, where the codebook C and the decoder DN learned in the first stage are fixed. The loss function for this stage is defined as follows. In this stage, the features from pre-trained encoder EL and decoder DN are fused, and the brightness-aware attention is applied to enhance the features. Brightness-aware attention first utilizes convolutional layers to compute a brightness threshold map for the input image. Regions in IL with brightness values below the threshold are set to 0, resulting in a brightness map M. M represents areas in L with higher brightness. By performing spatial attention operations between image features and M, the network's robustness to brightness is enhanced. The loss function for this stage is a simple MAE loss. And these are our experiment results. More details can be found in our paper. Thanks for your listening.